So the first speaker is Masnou from Lyon, and he will talk about Cahn-Hilliard-Willmore energy for non-oriented interfaces.
Thanks a lot for the invitation. Do you hear me correctly? Yes. Okay, thanks a lot for the invitation. I'm always very pleased to come back here in Pisa. So it's a joint work with Élie Bretin from INSA Lyon and Antonin Chambol from CNRS and Paris Dauphine University. Okay, so I'm sorry because maybe some of you have already heard part of this talk, and so there are a few things about phase field approximation that may be very familiar to some of you, but I'm not sure that it's totally familiar to everyone in the audience. So if it's too slow or too easy, or just tell me and I will skip. Well, from time to time it's too easy. Okay, so is anyone not familiar at all with phase field approximation? Everyone knows it. Oh, okay, you're not so familiar. So thank you. You saved parts of my talk. So no, otherwise, okay, I could spend more time on other parts. But so the main idea of the phase field approximation is to start from the observation that if you're interested in the approximation of some geometric energy associated with the boundary of a domain, so let's call here E the domain you're interested in, and for instance you want to compute the mean curvature flow of the boundary, of the smooth boundary of this domain. So the first thing that you do is that you approximate the characteristic function of this domain by a smooth function that takes value 0 outside, value 1 inside, and there is a transition zone which is called the diffuse interface where you smoothly pass from 0 to 1. So essentially the norm of the the norm of the gradient, or the modulus of the gradient is 0 inside, 0 outside, and in this transition zone it's around 1/epsilon. Okay, and so one of the celebrated geometric energy associated with phase field approximation is the so-called Cahn-Hilliard energy, but that's actually the first version of it was proposed by van der Waals more than 100 years ago. And so the idea is the following: you want to approximate, say, the perimeter of this set, so the area of the boundary. The smooth energy that you propose has two terms. One term which penalizes the gradient of the phase field approximation. So essentially it is supported in this diffuse interface zone. And there is another term which uses a potential W, typically a double well potential, with this parameter 1/epsilon. So what does it tell you? It tells you essentially that when epsilon is very small, this has to be very small, and for this to be very small, you need U epsilon to live very close either to 0 or to 1. So essentially you're trying to force your phase field to be in a natural phase, which is either 0 or 1. The very natural idea from van der Waals in 1897 or something like that was to say if you have a liquid gas interface or liquid vapor interface, say, you might say that there are some molecules which are in the gas state, other molecules which are in the liquid state, and there is an intermediate zone where you have intermediate status. But you want to force these molecules to be either in one state or in another state. So that's why this term. And of course, there is a sort of trade-off when you minimize this energy between this which penalizes, which forces the phase field to be smooth, and this term which forces the phase field to be either 0 or 1. Okay. And so classical things. in calculus separation. So you first extend your approximate energy in L1, and so you can directly work in terms of functional convergence in L1, and you can prove, this is a celebrated result by Modica and Bortola, you can prove that there is gamma convergence of this energy to a constant that depends on the potential you've chosen, and times the perimeter of your domain. So this function is actually, so perimeter is an extension. This function is actually exactly the perimeter of the set if you coincides, the limit function coincides with the characteristic function of the set, and plus infinity otherwise. Okay, so fine. One thing which is important is that to prove this gamma convergence result, you need to prove first the gamma lim inf result and the gamma lim sup result. For the gamma lim sup, you need to find a so-called recovery sequence such that the approximate energy of the recovery sequence will converge exactly to what you're interested in. And this recovery sequence is defined this way. Is there a pointer maybe? So for this recovery sequence, you first take the sign distance function to the set. So you need first to consider the sign distance function to your domain, which is positive inside, negative outside. You divide by epsilon, and you compose with Q, which is an optimal profile. What is an optimal profile is actually a minimizer under certain limit and intermediate conditions of your 1D energy. So essentially what you're saying is that you want to approximate the characteristic function of your set, but in a way such that around the diffuse interface, you do not spend too much energy. So this is why you're minimizing this energy. And so this is the optimal way to approximate in some sense. So of course, as epsilon is closer and closer to 0, this approximation will be sharper and sharper and closer to the characteristic function of U. But the approximation that you use here is very optimal in terms of energy. And so typically for this double well potential I mentioned before, I did not define it before, but this is the classical definition of the potential that you use for the Cahn-Hilliard energy. So this is the optimal profile, the exact definition of the optimal profile. So you have an explicit definition. And for this recovery sequence, you not only have functional convergence to their characteristic function, but also exact convergence of the approximate energy to the limit energy. Okay. So let's now go into the approximation of the mean curvature flow. So you have an approximation of the energy. Of course, usually when you approximate a function, it's very rare that the derivative of your approximating functions also converge to the derivative of your function. In general, it does not work. For this particular choice, it does. So let's consider an example of a mean curvature flow of a domain. So this is the evolution. And if you now look into the L2 gradient flow of your Cahn-Hilliard energy, you have this equation here, diffusion reaction equation. And if you start from an optimal smooth approximation of your initial set, this is the kind of simulation that you might obtain with a numerical approximation. I will go into a little bit more details just after. So it's very good approximation. The solution to this PDE is a very good approximation of this. In which sense? In the following sense, you consider your initial sharp set flowing by mean curvature. You consider the solution to the Allen-Cahn equation with this initial condition, and you consider its 1/2 upper level set. Then you can prove that this, so the solution to the Allen-Cahn equation stays very close to the optimal profile associated to this set. So there is no spreading of your approximation, that this set has a normal velocity, its boundary has a normal velocity which is exactly its mean curvature plus something that depends on epsilon. And you can prove for a short time the convergence of omega epsilon to the exact omega which is flowing by mean-curvature flow. This is a typical result that you get in Hausdorff distance. Okay? So the last paper I mentioned is 30 years ago, so quite old. Okay, now how do we obtain this kind of numerical results? So you want to simulate, to approximate the solutions to this equation. This is actually very easy. So on a Cartesian grid, you define a discrete approximation of your initial condition. You fix a time step. You handle implicitly the diffusion operator, because this is very easy to do with the fast Fourier transform, and explicitly the reaction operator. And so, of course, you can write that directly in this way. I will come back to that because it's important in connection with what I will say just after. Okay. The same thing, I will skip, well, not skip, but speak about that very quickly. You can do the same for the phase field approximation of the Willmore energy. You just observe that if you take the L2 gradient of your Cahn-Hilliard energy, then it's quite easy to say that it's a good approximation. Well, quite easy. You can observe that it's a good approximation of the scalar mean curvature of the boundary of your sharp domain in the transition zone, and this motivated this kind of approximation of the Willmore energy. So it started with contributions by De Giorgi and then several papers, in particular a paper by Bellettini and Paolini on the gamma-lim subproperty, and a paper by Röger and Schätzle on the gamma-lim-inf property, which is the most difficult to prove, and due to embedding conditions, you can prove that only in R2 and R3 for limit sets whose boundaries C2 and compact. So, okay. And it's the same recovery sequence that you can use for proving the gamma-lim sup. Fine. So the key aspects of phase field approximation is the fact that you replace singular energies with smooth energies. So in your approximation, everything is smooth. Now the function is smooth, the approximate functional is smooth. The gradient flow is also a nice reaction diffusion equation of order 2 for the mean curvature flow, of order 4 for the Willmore flow. You have for a certain number of energies, gamma convergence results, smooth global minimizers, approximate sharp global minimizers, thanks to this gamma convergence property. And you can do that for several phase field flows. So I just mentioned the mean curvature flow, surface diffusion, Willmore flow, multi-phase mean curvature flow, anisotropic mean curvature flow, and so on. And you can design very efficient numerical schemes. You can add various constraints, volume, area, inclusion, exclusion, surface tensions. You can also incorporate surface tensions, mobilities, and so on. So, but so far, what I presented is valid only for domain boundaries. I liked very much yesterday the epiphania word that were used, going back to Euclid. So it's really this idea you're considering the boundaries of domains. So this is what we've done so far. There are some phase field models which are compatible with what I call non-oriented interfaces, well, let's say more general interfaces that are not necessarily domain boundaries. If you think about the Ambrosio-Tortorelli phase field approximation for the Mumford-Shah functional, of course, it can handle also interfaces which are not necessarily domain boundaries. And there is also a paper by Lemenant, Bonivar, Lemenant, Sant'Ambrogio on the phase field approximation of, well, phase field approximation for the Steiner problem. But the thing is that for both these approximations, they are always coupled with some control energies. Here to force the fact that you try to connect points, and here to force the fact that you want to segment an image. So you always have these side control energies which are not adapted to the approximation of the mean curvature flow. Okay, so let me just illustrate what I mean by non-oriented mean curvature flow. Now, I have a situation where, of course, this is the boundary of a domain, but I don't want to see it as the boundary of a domain. So I'm just interested in the simulation of this interface, and I want to avoid considering what is inside or outside. It's not part of the consideration. So this is the kind of evolution that you can observe with exactly the same kind of assumption. So at every smooth point of your interface, the velocity is given by the mean curvature. And when you have multiple points, then you have the Hering's angle condition, which is the balance of force condition. So far, no, you don't. No, you don't. If you oh, that's interesting. So you consider the perimeter, so the length, and so you consider the derivation of the length by small perturbations. This is the definition of exactly the first derivative of the perimeter. And this gives you the variational definition of the mean curvature. And the variational definition of the mean curvature gives you not only an intensity, it also gives you a direction. So that's why you can do that in any codimension also. H is a vector, exactly. H is a vector here. Okay. So it's really the first variation of the perimeter gives you the direction, and it works indeed in any codimension. So here, yes. Oh, this. Yeah. No, wait. It can't be. Sorry. No, it's not. Not at all. So I don't know why I put that. So, so this will give. Well, I guess that this will give. I don't know. Sorry for the. No, this will be convexified, and then slowly evolve to points. Yeah, sorry. So this is another evolution. This evolution will give you that. Sorry for that. Yeah, of course. It's stupid. It's probably, you know what? It's probably due to the fact that all figures have the same name independently of the experiment. So it's just, yeah, it's stupid. No, of course, you have this result that tells you that there is convexification. And oh, sure. Okay, so far, no phase field approximation had been proposed for this flow, except in this case, for instance, you can of course see that as a multi-phase mean curvature flow. So you have both theoretical and numerical results on that. But the thing is that we really don't want to use the fact that you can have inner phases and outer phases. We don't want to incorporate the orientation. So in this work with Élie Bretin and Antonin Chambol, we proposed a new model. Gradient flow is a good candidate. How did we find it? And this is probably the so yeah. I'm not imposing anything. Two crossing line is not a stationary point. Two crossing lines should separate into two triple points. It's not difference. That's the point. The thing is that the difference is in the approximation model. So we don't want to plug in a multi-phase field approximation. Let me give you an example. If I give you now boundary condition, typically the plateau problem, I can't treat that as a multi-phase problem. So to answer maybe more precisely to your question, if it is compatible with a multi-phase approximation, the flow will be the same. But it can be extended to other situations for which the multi-phase approximation cannot be used, because you cannot define inside phases and outside phases. But of course, we want it to be compatible when it's possibly compatible. So how did we find this flow? By trying first to learn the mean curvature flow with a neural network. okay, that's a good point. That's a good point. So start, for instance, from a square. Then, of course, you might find. So I'm terrible for drawing things, but what I want to say is that, okay. Okay, so maybe, how does it work? Yeah, okay. So here it's easy, but there are other situations where you have two possibilities actually. And so in that case, in the numerical approximation, there will be a choice. So the approximation, actually the initial condition, for instance, the approximation, the numerical approximation error will force a choice. But in theory, for the flow, of course, you might have bifurcation. There is no uniqueness in general. In these situations, there is no uniqueness. You know that. No, our result is so far only a gamma convergence result. We can't prove anything for the flow. So, of course, and for the flow, the thing that we'll be able to prove is what has been proven for the phase field approximation of the mean curvature flow, which is in a short time for smooth flow. So the thing is that indeed, in the case where you have, so this is the typical example for the Willmore energy, the phase field Willmore. So the phase field approximation of the Willmore energy will give you this kind of solution. This is possible, which is related to what you're saying. Why that? Because these are nodal lines for smooth, singular nodal lines for smooth approximation of the Allen-Cahn equation. And there is the Allen-Cahn equation, well, the Allen-Cahn term in the phase field approximation of the Willmore function. And of course, this is in terms of Willmore energy, this has infinite energy. In terms of varifold Willmore energy, this has finite energy. So it depends on the model you're using. But for the, okay. So yes, there might be bifurcation. So let me maybe, so I have till 10 to 10 or something like that. +5 if I like. Okay, no, don't tell me that. It's better. No. Okay. So just to come back to the previous slide, before presenting you the model, whose analysis is, well, it's nothing, absolutely nothing spectacular. But what is interesting is probably the way we found that. So we found that first trying to approximate, at least numerically, the mean curvature flow using neural networks. So what is a neural network? Very roughly speaking, a toy model for neural network is the composition of a certain number of applications, which are composition of affine maps and a nonlinear map, which is called an activation function. So typically, in this composition of many layers, these linear map and the bias are trainable operators, so they depend on coefficients theta I that are free, and there might be a lot of them. And usually, the activation function is a fixed pointwise. So if you have a vector, it acts component-wise. Is a fixed pointwise or local nonlinear operator. Typically, what is called one of the most famous activation function is the so-called ReLU, rectified linear unit, which is just this. But you have also many other examples that are used and that have been studied in various contexts. Okay. So now, this is the definition. So it's an operator that depends on many parameters. And what does it mean training a neural network? It means usually that you are given inputs and ideal outputs, a certain number. Imagine that these are images where you want to decide if this image has a cat in it. Okay, so you have millions of images, and each time there is a cat, the result should be 1. If there is no cat, the result should be 0, for instance. This is the simplest example. So what you're trying to do is that on these millions of examples, you're trying to tune your parameters, trying to force that the output of xi with your f theta be close to the ideal result that you want. This is training. This is what training a neural network is. So of course, you're using what is called a loss function to penalize the difference between this and the ideal result. This is the situation of what is called a supervised training. There are also unsupervised training, but I won't enter into this detail. So now, what about learning flows, typically geometric flows with neural network, or learning PDEs, for instance? The first approach is to consider that this map, f theta, is actually the solution to your PDE, let's say. And so you know the exact value of the solution, or good approximation of the solution on particular choices of t and x. And so you try to optimize the parameters of your neural network using these ideal values that you have. And usually you also compose with adding in the error metric initial boundary condition, plus if you know what is the underlying PDE model, where you can also use using automatic differentiation, the exact PDE if you want to force your solution to satisfy the PDE. So this is a very classical approach. If you look at, so there are tremendously many papers now on that, on the PINS, physics-informed neural networks. It's, well, it's not that spectacular, actually. It works, but I mean, there are many problems with that. So there are some situations where it works very well, other situations where it does not work so well, but there is an intense research activity on this. It's really, really interesting. The second approach is to consider that your input is the solution to your problem at a time t, and your output should be the solution of your problem at a time t plus delta t. So the network is just one step of a discrete semigroup associated with your problem. So what you're trying to do is to train the parameters of your neural network on many pairs, u at time ti, u at time ti plus dt. And usually, of course, you have discrete approximations of these solutions. Whereas here, so here you depend on a grid. In general, here you might not depend on a grid. This is quite interesting from this point of view. Okay, so let's see how we can do that for the learning of the oriented mean curvature flow, so the mean curvature flow of domain boundaries. So the key point is that you want to train your network on exact evolutions. So this is not an exact evolution, this is an approximation. I will tell you what kind of exact evolution we use. And if this is an exact evolution by mean curvature flow, I take the optimal phase field approximation associated with this exact evolution. So really here, I do insist on the fact that this is a real exact evolution, and I'm taking the an optimal implicit approximation of this exact evolution, okay? And we train a network to approximate one-time step evolution. And for the unoriented mean curvature flow, we do the same, except that instead of working with the optimal profile, you remember that Q is the 1D optimal solution to the 1D energy. But if you just consider the derivative of Q, Q prime, the derivative of Q is localized around, actually around 0. And so if you compute Q prime of the same thing, the distance function to your exact mean curvature evolution divided by epsilon, then you have indeed a smooth approximation of only your diffuse interface. Okay? And you train another neural network to learn that. So what are our exact evolutions? For the mean curvature flow, the structures for which we really exactly know the evolution are spheres. Of course, in dimension 3, we can also use cylinders. We have the exact evolution law for cylinders. So what is nice here is that if I give you a phase field approximation of a sphere of radius Ri, I can compute the exact sphere at time t plus delta t using exactly this formula here. So I can do that with phi equal to q and with phi equal to q prime. So this is, with that training data set, we're going to learn a first neural network. With that other training data set, we're going to learn another neural network. It's not the same evolution, of course, so the networks are separately trained. Okay? Is it all right? So now, of course, we have to say that we want the neural network to be a very good approximation of the discrete semi-grip. So we need to use what is called a loss function, so a penalty energy. And so on all your training data set, you're going to compare the output of your neural network with the ideal output that you know, because you know how a sphere should evolve. Okay, and this is for one step, but you can also, if you want to stabilize more, do what is called a multi-step loss function. So you do that, let's say, for 5 consecutive steps, and you penalize the successive action of your neural network, and you compare with what is the ideal result you should obtain. Okay, classical things now within Python environment for the training of neural network. You can use what is called a mini-batch stochastic gradient descent algorithm with adaptive momentum. There are many, many methods that have been proposed, Adam, Adagrad, RMS-prop, and so on. All of them adapted to the fact that your energy here is highly nonlinear and highly non-convex. And so you have critical points absolutely everywhere. So you need to have really strong descent methods that are able to handle small local minimizers. It works pretty well, actually. Okay, so what are the... So I did not mention the structure of our neural network so far. The thing which is interesting is that we did not want to have neural networks which are black boxes. We wanted to have neural networks which are really adapted to our problem. And the inspiration came from the classical numerical approximation of the Allen-Cahn equation. So you remember that the Allen-Cahn equation is the phase field approximation of the mean curvature flow. So this is the scheme I presented earlier. Remember that it is implicit for the diffusion term and explicit for the reaction term. And so the exact one-step evolution is this one. And of course, when you see it that way, you pass in the Fourier space, you come back. So this is exactly as considering a convolution operator with a nonlinear operator, which is this one. So our idea was really simple. Okay, let's try to train a neural network where you have a diffusion operator, which is actually a convolution operator, combined with a reaction operator. So you might observe that the order is not the same. That's correct. The order is not the same. Initially, it was the correct one, and then there was a bug in the code, and we tried the other way, so starting first with the diffusion, then the reaction, and the result is better. Of course, this is for one step, and if you want to do several steps, you have to iterate the action of your neural networks. Let me just tell you a little bit more about these two networks here. So, okay, discretization grid and so on. As for the diffusion neuron, it is based on a discrete square nucleus K. So you have a convolution. So it's a linear operator, a convolution operator. And the size of this convolution kernel depends on the rate square root of the time step divided by the space step. And the reaction neuron is a 1D multilayer perceptron, which is this one. All these points are Gaussian function. And here you have affine combinations of all these results. So 8 Gaussian function, 3 Gaussian function. The difference between what I said earlier, where you have trainable affine operators plus a non-trainable reaction operator, here the affine combinations are trainable also. So that means that combining this convolution operator with this reaction operator, which is a pointwise action, it acts on every really on every pixel of your approximation. It has 336 parameters. If you compare with ChatGPT, who has, of course, ChatGPT does much better things than that, but I mean, it's really not a lot of parameters. It's really designed for the problem. Okay, and you can also try, once you have this structure here, you can also try to have higher order neural networks. Typically, so this is the base brick, and you can also try to combine with other diffusion neurons and reaction neurons, and here it's just R plus identity. The inspiration comes from residual neural networks. Well, we tried several combinations. So what is interesting is the following. This is the plot of the loss function along the iterations for, in blue, the first order neural network, and in orange for the second order neural network. So it's really oscillating. This is normal. It works pretty well. Okay, and these are the kind of result that you get. So this is the classical numerical approximation of the Minkowski flow with the Allen-Ken equation, and these are the kind of approximation that you get with our neural networks. Of course, you iterate the result. So you were asking about the evolution of the. It's this one. It's a logarithmic scale. No, I'm not sure it's a logarithmic. Why? Oh, no, it's not exponential. It's slower than that. Oh, 10 minus 1, 10 minus 2, 10 minus... I can't read either. It's quite slow, the evolution. Okay. What is interesting is that if you compare, so what should be the ideal volume of an evolving disk? You know the law, and you can compare the result that you get. So the error should be 0, and this is what we get with the first order and second order operator. So the error remains very low, and if you compare with the classical numerical approximation of the Allen-Ken equation, the error is larger. So it means that the trained networks lead to more accurate numerical schemes than those derived from the discretization of the Allen-Ken equation. That's not surprising. So we decided to relax the composition of a convolution operator and a nonlinear operator. If you relax the parameter, you should do better, of course. Okay, what about the non-oriented Minkowski flow? This is more interesting. You see that the training here is more difficult. It's very slow here compared with the previous one, and the second order is not so good, and then is better. Okay, what is interesting is the result you get. This is the evolution with the first order neural network of just a disk, and you see that it disappears. So it does not work. So the first order neural network is not adapted to that. The second order neural network is adapted. And okay, you can compare in terms of energy. It's excellent for the second order one. It fails completely for the first order one, of course. So you see the difference. For the oriented Minkowski flow, using either the first order neural network or the second order neural network is fine. For the non-oriented neural network, you need to go into higher order. Why that? So let me just show you first some simulation we obtain. No, this is stupid. This is again the same error. Okay, I'm sorry for that. So the question is the following. We identified a second order, not very much time now. So we identify a second order neural network that approximates fairly well the Minkowski flow non-oriented interfaces. Is there behind a second order variational model? So this was the starting point of our, and so the answer is yes. It started from an observation by Elie Bretin that if you take the optimal profile associated with the classical phase field approximation the Allen-Cahn equation. And so you know that Q prime satisfies this equation and the second derivative of Q satisfies this one. If you keep derivating, then you get that the third derivative of Q is a solution to this equation. So it means that minus Q prime is a solution to this second order equation where F now is not the double well potential I mentioned before, but it's a potential with two wells, fine. But you see that here the derivative is 0, but not there. So that's the major difference if you compare with W, where really you have this double well, smooth double well, etc. Okay? So, of course, observing this, because minus Q prime is a solution to this is a second order equation. So a natural PDE associated with this second order equation is actually the Allen-Cahn type equation, except that here, instead of W prime, you have this F prime, your new potential. Fine. But as we observed with the second order, with the first order neural network, if you just use that as an approximation, it won't work because the diffuse interface disappears. The profile is not preserved along the iteration. So you need to force the preservation of the profile. And this is what we propose to do, adding a second order phase field approximation, which is actually phase field approximation of the Willmore energy, with a parameter sigma epsilon divided by 2 epsilon that guarantees the stability of the profile. Once again, I want to insist on that because it's maybe no. Once again, I want Q prime to be a solution of this. So I want to preserve that, but I have to force it. And to force it, we're using this term here, where epsilon squared divided by sigma epsilon goes to 0, and this guarantees the stability of the profile, and it controls the persistence of the Willmore time term in the limit energy. If you want to make it disappear, just have sigma epsilon that goes to 0, and it will disappear in the limit. So the L2 gradient flow of this energy is actually the classical perimeter plus Willmore phase field approximation, except that you have this, and you can study the evolution of that. You can study, sorry, not the flow so far, we are far from that, but we can study the gamma convergence of this energy. Okay, so let me skip that. So far the analysis works, our analysis works only in dimension 1 and in higher dimension for radially symmetric approximate function. We have difficulties for the situations where it's not radially symmetric. And what we can prove is the following. It's really based on a careful study of what is called the discrepancy function. You might remember, for those of you familiar with the phase field approximation, that this is the key aspect when you try to optimize the energy of your diffuse interface. You have to find a good trade-off between these two terms. And so you want to have this as small as possible in absolute value. So this has been used a lot, in particular for the study of the Cahn-Hilliard equation, but also for the study of the Willmore phase field approximation. And this is the same for us. I will skip that. So I just want to insist on several things. So in dimension 1, we are able to prove that if we have a sequence of smooth functions whose approximate energy is uniformly controlled, then we can prove that if we look at the mu epsilon, so the diffuse mass energy, it does converge to a limit measure, and this limit measure in dimension 1 is supported on a finite collection of points. This limit measure can be decomposed this way, so it's an illustration of that. For epsilon small, u epsilon is very close to 1/4 near every of these points, and we have also a lower limit for the energy. What is more interesting is that in higher dimension for radially symmetric function, we have the same kind of result, except of points. Now our functions are concentrating, so I want to insist, I have a figure after, are concentrating on circles, a finite number of circles, so I'm working out of zero, finite number of circles, and I also have a lower control of the limit energy, where you have the perimeter plus the Willmore energy of your spheres times sigma 0, which is the limit of sigma epsilon. So the key is this assumption here. It is a key to control the discrepancy function I mentioned before. So let me maybe illustrate what happens. The first steps of the proof is very classical in phase field approximation. You just get from the control you have the fact that your phase field functions are converging almost everywhere to some limit function u, which takes values 0 and 1, 4 almost everywhere. Fine. And the thing is that you can prove a uniform control of the pointwise discrepancy. So this uniform control takes into account the energy and this term here. You remember in our assumption epsilon squared divided by sigma epsilon goes to 0. So this goes to 0. So it means that we have locally control of the discrepancy. And then you just physically understand what happens. So if you have a control of the discrepancy, you observe that, so f is 0 here and there, but the derivative of f is not 0 here. So that means that when you start being above a certain step, because of this, you will keep going up, okay? But then, when you arrive there, you have, and you start to stay a little bit quiet, so you do not move too fast. So the second derivative is small, but f prime is not small at all. So f prime is not small at all, so it forces you to go down again. So you can't stay very long above. So that's the difference with the classical phase field approximation, where because you have this double well with zero derivative, you can stay quite long, for quite long, I mean, on a domain, really, you can stay above, so almost equal to 1. Here, because of that, because the derivative of f is non-zero here, you can't stay very much close to 1/4, because you're penalizing this term here. Let me show it again, because you're penalizing this. So if this is small to 0, this is, of course, and this is non-zero, this is very small, so you're penalizing that. So using this control, pointwise control of the discrepancy function, the thing is that we're able to prove, let me skip that, we're able to prove that the characteristic size of a diffuse interface is controlled by epsilon. It's quite small. So you go up and you don't stay much. You go down almost immediately. Then you can evaluate the mass of a diffuse interface. So going up costs you CF divided by 2, going down CF divided by 2. And because you don't stay very much above, this is small o of 1. Okay, and there are finitely many diffuse interfaces and so on. So this is an illustration of the kind of concentration phenomenon that you will have. So in higher dimension, instead of concentrating on points, of course, you will concentrate on circles, and you might have several diffuse interfaces that will concentrate on circles, but all of them are capital O of epsilon. And so, and then you prove a control of the limit Willmore energy, etc. Okay, fine. So a few remarks before stopping. Sorry, I'm a bit long. The Willmore type term is fundamental to prove both results, but its limit does not appear in the 1D result. The same construction proposed by Bellettini and Paolini to prove the gamma-ellipse property for the phase field approximation of the Willmore functional of smooth sets can be applied here. And a gamma convergence result follows. So the gamma convergence, let me just state here, we are proving that it's interesting here because our approximating functions are going to 0 almost everywhere. So you see it's a gamma convergence result where you start from pairs of functions and measures, and in the limit you have 0 for the function And for the measure, you have an accumulation of things which are concentrated on spheres. And so we have a gamma convergence result, and that's all. Numerical scheme, let me skip that, and some result that we get with this new phase field model. It's interesting because you remember I told you that epsilon squared divided by sigma epsilon should be close to 0. It should converge to 0, sorry, for the approximation to work. And of course, if it's too high, it's not able to preserve the profile. So it has to be small. If it's small, then the profile is preserved along the iteration. It works also if you have singularities. It works in higher dimension. And you see that there is no topology change due to this Willmore term that preserves actually the topology. Triple junctions, okay, and surprisingly, it works also in higher codimension. We don't really know why. The Willmore term is also able to preserve, so to prevent from the disappearance of the diffuse interface. And the flow is compatible with what should be the ideal flow. Okay, this is an evolution also. I can show you an evolving film. I suspect that it's because I should compile once again to get the result. Maybe I should do that during the questions. Okay, just the conclusion. Sorry for being a bit long. What is maybe interesting in our path is that we follow the modeling path, phase field model, neural network, new phase field model. So several questions remain. Of course, what about the non-radially symmetric case? We're thinking about adapting the variable techniques proposed in a paper by Röger and Schätzler for the Willmore phase field functional, but it works only in dimension 2 and 3. What can be said about the gradient flow? Of course, we have numerical simulation, but it's just numerical illustration. We don't have any proof of convergence. That's the major difference with the classical phase field approximation of the oriented mean curvature flow. What about higher codimension? Our approach is intrinsically related to codimension 1. So in higher codimension, normally we should have some a profile which is slightly different, but it seems to work. But well, there are things we need to understand. How does the flow compare with the one simulated by the neural network? And what can be said about approximate multiple points along the flow? And that's all. And maybe I should recompile the file to get the simulations if you're interested in that. But sorry, I've been a little bit long. Thank you very much for your attention.
Any more questions?
I was wondering so radially symmetric means radially symmetric or surfaces of revolution, because you had this example with the dumbbell.
Ah, okay. Radially symmetric means that for the analysis, we're able to prove gamma convergence results, assuming only that we are in a radially symmetric case. But of course, once we have a variational model, we can compute the gradient flow and try to do a numerical simulation of this gradient flow. So this numerical simulation is for any context, of course. And it seems to work as well, but our analysis works so far only in the radially symmetric case.
So again, by this dumbbell example, you are saying that the Willmore prevent a topological change there. So
yes,
can you comment on that? So it's a numerical
no,
feeling you have? No.
It's really due to the fact that when you start going up, due to the control of the discrepancy and due to the fact that the second derivative is associated really with this f prime strictly non-zero, you will, no, sorry, there are two things. The fact that there is the discrepancy at the first order and the discrepancy at the, no, there is only a discrepancy at the first order, but you will go up necessarily and you will stay above, but not for very long. But you cannot break down this. So it won't disappear, actually. So you cannot make that disappear. It really had to go up and then to go down. But if you go up, you really go up. So you might concentrate these bumps, but you might not remove them. It's really due to this discrepancy.
Okay. Yeah, Felix was first.
Thank you. So I have a question about the first part. I mean, when you use a neural network for the traditional Allen-Cahn equation.
Yes.
So this reminded me of something which Craig Evans said, that the thresholding scheme, in a certain sense, can be already interpreted as a neural network, because
Exactly.
you're doing a kind of convolution and a thresholding step.
Yes.
So could you, with the same philosophy instead, but not putting Allen-Cahn in between, kind of design better nonlinear stencils for the thresholding scheme by learning the stencil on kind of standard evolutions like those of the sphere?
Yes.
And perhaps this has already been done because it's such a kind of natural idea, and stencils and linear problems and transport problems have already been learned by looking at geometric objects.
Yes.
So it sounds much simpler than what you're doing, because you're putting kind of Allen-Cahn in between, instead of right away thinking in terms of this thresholding scheme, which has neural networks built in.
So especially because the analysis is much deeper for the convolution thresholding scheme, and indeed you might generalize to many situations. Indeed, I think Selim Ezedoglu did try to use also neural networks to optimize the stencil and so on, and I think Antonin Charbel also worked a little bit on that. One of the problems with the convolution thresholding schemes in terms of numerical approximation is really the fact that you threshold. So at some point where the evolution is very slow, the fact of thresholding actually stop completely the evolution. So this is the major difference, I think, with the phase field approximation. The fact of having something which is smooth makes that your evolution keeps going. Instead, on a very concrete, from a very concrete viewpoint, when you use convolution thresholding schemes, you are at some point stuck at some resolution, because everything goes fine at the continuous level, but at the discrete level, the fact of thresholding is too strong. It's too sharp. So you're absolutely right. It should be better, and you should be able to optimize the stencils using neural network. One of the drawback, I think, not from the approximation viewpoint, from the numerical viewpoint, is this fact that you're threshold. This is I think a major problem, that in practical applications, you see the limitations. As soon as you want to be very accurate locally in the evolution, at some point you do not evolve anymore due to that, because you stop the evolution by thresholding.
Pinning.
Yeah, exactly. But it's a numerical pinning. It's not a theoretical pinning. It's a numerical pinning.
There's also a version of thresholding where you distance functions.
Yes, but you have to recompute each time the distance function, and this, numerically speaking, is quite unstable, actually.
Yeah, but you learn it. You don't then after learning it, you wouldn't do it.
Okay, so you say you learn the resistancing. Yeah, this has been done, in particular in computer graphics, a lot. I don't know these situations where it's interesting. I don't know situations where it has been applied. Okay, I understand what you mean. So you use neural networks for redistanciation and also for computing the optimal shape of the stencils. Yes, it could work, indeed. But probably I would say that the thresholding should be replaced by a sort of soft thresholding, something which is not that sharp. But I absolutely do agree with you. If I just have 1 second to show you the final evolution of, I'm pretty sure now it. No, well, it's my computer. It was working and it's not working. I don't understand. The files are there. So it was working at the hotel. It's not working here. So the files are there. Okay, sorry for that. I don't know, technical.
We can retry after the break.
Okay.
Yeah. Various things of the new phase field model you proposed remind me of like phase field models for crack propagation. besides the fact that they are coupled to elasticity fields and so on.
Yes.
But
Do you mean in the Mumford spirit?
yeah, right. In this spirit, I mean, you have this modified potential. You have some sort of regularization. There are different
Yes,
and so on.
Sorry.
Do you see any relation to
yes.
the-
Okay. This is what, when I mention Ambrosio Tortorelli, this is really related to what you're saying, the Frankfurt-Marigot model, which is really related to Mumford. And you have also, you have many works on that for the phase field approximation. So the problem is that it's exactly like for the Mumford functional. If you just take the phase field approximation of the perimeter, it gamma converges to 0. So you need to associate these with other terms. So for the Mumford functional, it's the penalization of the gradient outside, etc. For the brittle fracture modeling, it's the fact that you penalize the symmetrized gradient and so on. So you always need these side energies that will make. So there is a sort of trade-off between all these terms. But here, we don't want any trade-off. We don't want to associate our geometric energy with another energy due to elasticity or whatever. And if you do it, then it's not the mean-curvature flow anymore. It's another flow. So the gradient flow of the Mumford functional is not the mean-curvature flow, of course.
No, of course, but isn't
But
this
I
this
understand.
additional thing not? I mean, now you add this kind of Willmore term, isn't it also some additional thing?
You
which
could
doesn't-
okay. What you're saying is that is it possible to combine the Willmore approximation term with brittle fracture approximation, for instance? Yes, of course. If I can add something in the Mumford, in the Ambrosio Tortorelli approximation or the phase field approximation of brittle fracture, as you mentioned, one thing which is a problem is indeed the fact that actually your solution is not smooth where you have your interface. Indeed, so now in our case, it's smooth, and of course it would be smoother adding a Willmore energy term. But then what you say is fine if indeed, like in our case, you make this Willmore additional term disappear in the limit. So you have a distortion of your geometric flow, but you wanted the distortion to be not too strong.
Okay, maybe one last question.
Yeah, thanks very much. So I had a question about the neural network part. When you were training it, you said you just used the spheres. Did I understand that correctly? You just use spheres?
Oh, okay. In 2D, we just use circles. In 3D, use spheres and cylinders.
I see. Okay. And
But I mean structures for which we really exactly know the exact evolution.
right. So something like the anginate oval, not oval, sorry, that's Ritchie flow. The anginate self-similar torus. If you use more things that you really know, does that help the?
Yeah,
It
of
does.
course it does.
I see.
The thing with circles and spheres that it's very easy to plug that
Sure,
into.
sure.
But of course, if you add other examples, okay, we did that also for the anisotropic mean curvature flow.
Mm-hmm.
So using, instead of spheres, we use the wolf shapes associated to the anisotropy. And then it becomes to be a problem because if we don't have enough examples in our evolution, then the flow which is simulated is not the correct one.
Mm-hmm.
So that's an issue indeed. So you need more wolf shapes in some certain situations. Typically for unsmooth anisotropy, we try the situation where, so we have, well, let's take a square. We have the exact evolution of the square with the anisotropic mean curvature flow. And then we rotate the square and the evolution was wrong because actually in the learning, in the training step, nothing was said about the evolution of diagonal directions.
See.
Yeah. And so that's the problem. Instead, in the isotropic case, you have circles or sphere, whatever. So every directions are represented. So if I give you this example of one circle, actually you have millions of examples with all possible directions. It's very rich. In the anisotropic case, it's not rich at all, and that's a problem, indeed.
I see. Okay. Thanks.
And maybe we can ask further questions later and thank Simone again for the moment.
Thank you.
So our second speaker is Maria Giovanna Mora from Pavia, and she will talk about shape transitions in frustrated elastic ribbons.
Thank you. So first of all, I would like to thank the organizers for this invitation. I also want to apologize since I was able to join the conference only on Wednesday. So we are in the middle of the teaching semester. Unfortunately, I'm teaching a lot. And so it was really impossible to come earlier. So I'm sorry for that. So what I'm going to talk about today is actually motivated by work from Eran Sharon and his group. And it's about a change of shape in ribbons driven by growth. And so everything, well, all the results I'm going to show are joined with Sima Or from the Hebrew University. Okay, so as a motivation for this work, I would like to start from this picture taken from a paper by Eran and collaborators. So in this picture, you can see some macromolecules that live in a solution. And so as time evolves, these molecules aggregate and they become bigger. And in doing so, they change shape in a rather significant way. So after 24 hours, they look like long twisted strips. Then after 1 week, they look more like two-dimensional surfaces in a sense, and have this sort of helical structure. And then if you wait long enough, they close up into tubes. And so what is interesting of this phenomenon is that, well, you are observing a morphological evolution, so a change of shape. But somehow the molecules are not changing. So the internal structure of the molecules is always the same. And so what changes as time evolves is that they are becoming wider. And so the change of shape is driven by the growth of these molecules. And so this is an interesting phenomenon that you can observe also in other examples from nature, for instance. And here are just two pictures of a seed pod and of a desertic plant where you can observe a similar phenomenon. And actually the shapes we see here are very similar to the ones of this helical structure that we see in the macromolecules. Okay, so now, well, the first question is how can we model this phenomenon? So how can we explain this mechanism? And, well, last but not least, what can we prove about it? So it may be that now I'm going to, so the things that I'm going to say somehow have been already said in previous talks during the week, so I wasn't there, so I don't know exactly. So I apologize for that. I mean, if there are repetitions, I'm sorry for that. Okay, so let me start by pointing out some of the key features of the structures we saw in the previous slide. So the structures we saw can be modeled as ribbons in the sense that all the structures we saw are both thin and narrow, but they are thinner than narrow. So we can imagine that we have two scales, two geometric scales. T stands for the thickness and W for the width. They are both small, but T is much smaller than the width. So these objects are called ribbons. And well, very often these structures have some geometric incompatibility in the sense that they have an internal geometry that is incompatible with Euclidean space. So what I mean is that it may happen that so these materials are such that if you look, I mean, locally, so locally there is somehow a preferred configuration that the material would like to achieve, but all these local preferred configurations cannot be combined together in a single global deformation. So they are incompatible in this sense. So this is what internal geometric incompatibility means. So the presence of this internal geometry is usually due to some inhomogeneous process, like for instance growth, plasticity, or other phenomena. And so because of this geometric incompatibility, even if there are no external loads applied to the material is in a state of stress. It's pre-stressed. Okay, and so the main question is to understand how this local intrinsic geometry affects the global shape that these structures achieve in space. And well, we already heard in Antonio's talk yesterday some applications of this phenomenon. So this is very interesting from the point of view of applications. So for instance, in the context of shape programming, because if you understand how the local geometry affects the global shape, then in principle you can somehow design self-shaping devices. So devices that can attain a desired shape autonomously. Okay, now ribbons are particularly interesting, basically because they have two scales. And so according to the relation between thickness and width, you can observe at equilibrium rather different shapes, even if the geometry, the intrinsic geometry is the same. So what I mean is that if you have a material with some geometric incompatibility, and from this material, you cut two ribbons, one rather wide and one rather narrow. Well, in many cases, these two ribbons at equilibrium will have a different shape, even if they are made of the same material. And so when this happens, one speaks of shape transition when you pass from wide to narrow ribbons. So, however, a shape transition doesn't always occur. It really, I mean, it strongly depends on the geometry you are considering. And so the question is, well, when we really see a shape transition, so when does a shape transition occur? And if it does, what is the critical scaling, so the critical ratio between the two parameters, thickness and width, at which we observe a change of shape. So these are the main questions. Okay, so now to understand a little bit how we can explain this mechanism, this behavior, I would like to start with a two-dimensional simplified model. This is not the one we considered with C, but it's the model used in the physical literature. And I think it's a good model to start with to understand how this mechanism can be explained. So in this reduced model, the ribbon, which in principle is a three-dimensional object, is modeled as a two-dimensional strip of height W. And the internal geometry is encoded into two given two prescribed tensors, which represent the target metric and the target curvature. So they describe somehow the local preferred configuration of the material. Okay, so now a deformation of the strip is simply a map from the strip into R3. And the energy of a deformation is given by this expression. So it's the sum of a stretching term and of a bending term. So the stretching term measures the distance between the target metric and the metric produced by the deformation. So that is the first fundamental form. While the stretching term measures the distance between the target curvature tensor and the curvature tensor produced by the deformation, so the second fundamental form. So here, when you see this notation, so I always mean the averaged integral. So I always divide the integral by the measure of the domain of integration. Okay, so the parameter T, the thickness, I mean, it's not in the reference configuration anymore because here the ribbon is modeled as a two-dimensional strip. So the thickness parameter shows up in the energy. So the bending term is multiplied by the factor T squared. So T is the thickness. So where does this energy come from? Well, maybe there's no need to say it in this audience, but I'm going to say it anyway, for maybe someone is not familiar with this kind of energy. Well, this energy can be deduced as an expansion of three-dimensional nonlinear elasticity, an expansion, a formal expansion in terms of the thickness. And so from a formal expansion, you can see that, in fact, the bending energy scales as t squared, while the stretching energy is of order 1. Actually, you can also justify somehow rigorously this kind of expansion in terms of gamma convergence. And this goes back to the beautiful results by Stefan Müller with Gero Friesek and Dick James in the Euclidean case. And then there are contributions by Marta Lewicka and co-authors in the non-Euclidean setting. Okay, so this is the energy. And now what happens when we try to minimize this energy? Well, it's clear that if we can find a deformation achieving both the target metric and the target curvature, then on this deformation, the energy is 0. And so this is a minimizer, and we cannot do better than that. However, this is not always possible because, and this is where somehow Gauss comes into play, because, well, the first and second fundamental forms of a surface in R3 are not independent, so they must satisfy some compatibility conditions. So more precisely, 3 equations. So the first equation is the Gauss equation, so relating the determinant of the second form to the Gaussian curvature that you compute starting from the first form. And the 2 Codazzi equations that basically state a symmetry property of the covariant derivatives of the second form. So the metric and the curvature produced by the deformation must satisfy the Gauss and the Codazzi equations, while the target metric and the target curvature may not satisfy these conditions. So because they are not necessarily the first and the second fundamental forms of a surface in R3. And so when the target tensors do not satisfy these compatibility equations, so one speaks of geometric incompatibility. And so in this case, the energy cannot be 0 on any deformation. And so one says that the ribbon is frustrated because it wants 2 incompatible things, so a metric and a curvature that are not compatible. Okay? Okay, so assume that we have incompatibility. So the target metric and the target tensor, the target curvature are not compatible. So what can we expect when we minimize this energy? So let me look at an example. So actually, this is the example we started from, so the one of the macromolecules. So in this example, there is a geometric incompatibility at the level of the Gauss equation. So in fact, in this example, you can estimate the target metric and the target curvature. And what you have is that the target metric is simply the identity. And so it's a flat metric with 0 Gaussian curvature. So for this metric, the Gauss equation simply says that the determinant of the second form should be equal to 0. But this is not the case here because the target curvature has this form where lambda is a non-zero constant. So the target curvature has negative determinant, and so the Gauss equation is not satisfied in this example. Okay, so what can we expect when we minimize the energy? Well, what you can do is to construct a deformation for which the first fundamental form is close to the identity, which is what we would like to achieve. But if you allow for a non-zero determinant of the second form, let's say on the midline of the ribbon, then this contributes to the first form in this way. So this comes from the Gauss equation, basically. So here, x2 is the variable in the height of the strip, so it's small, it's of order w. Okay, so now let's plug these ansatz into the energy. And so what we see is that the stretching energy is, because of this structure, is of order w to the power 4, unless this determinant is 0. while the bending energy is of order t squared, unless the second fundamental form coincides with the target one, with the target curvature. And the point is that these two terms cannot be both equal to 0 because of the Gauss incompatibility. So when we minimize the energy, we have a competition between these two terms. So more precisely, if T, which is always much smaller than W, is much bigger than W squared, then it's convenient to achieve the target curvature so that the energy is pure stretching, and so it's of order W to the power 4. While for T much smaller than W squared, then it's convenient to achieve the target metric so that the energy is pure bending and it's of order T squared. And so what we see here, it's a shape transition when T is of order W squared. And so the transition, somehow, we see it in these different geometric conditions. So let me notice that so this first somehow regime corresponds to a ribbon where T is rather large, or if you want, W squared is rather small. So it's a thick ribbon, or if you want, a rather narrow ribbon. While the second case corresponds to a ribbon which is rather thin, or if you want, rather wide. And by the way, these geometric conditions describe pretty well what we see in the first two pictures of the experiments. And we will see in a moment that, in fact, this small heuristic description is the correct one every time the incompatibility comes from the Gauss equation. Okay. Now, summarizing what we can expect. Yes?
Sorry, so the line in the center would become horizontal in the cylinder, would go this way?
Well, what happens when you pass to this case, I think, is that W becomes rather large.
Okay.
And so somehow the description is close to that of a two-dimensional object.
Okay, thank you.
It's not somehow a ribbon anymore. Okay, so summarizing from this heuristic argument, we can expect that according to the relation between thickness and width, we should have two regimes. So one bending dominated, where where the target curvature is matched at stretching cost, and this should be the case for narrow ribbons, and a stretching dominated regime where the target metric is matched, so isometries are favored at bending cost, and this should be the case of wide ribbons. So in particular, we expect wide ribbons to be more isometrically constrained, so to be more constrained. And this somehow is reasonable because, well, a wide ribbon should behave more like, so more closely to a two-dimensional object, to a surface. However, this is not really the picture, so the situation is more complicated than that. And this was observed in a paper by Eran Sharon and Simor and collaborators. So in this paper, they, exhibit some experiments, so some, real-world frustrated ribbons produced in the lab. So I have a picture in the next slide of this, ribbons from the lab. They also perform some formal expansions on the two-dimensional energy. And from these experiments and these formal asymptotics, what they show is that, well, this description is the correct one for ribbons that are incompatible at the level of the Gauss equation, where you should observe a shape transition when T is of order W squared, so exactly as in the example of the previous slide. While when the incompatibility is at the level of the Codazzi equation, the situation is much more complicated in the sense that some ribbons do not show a shape transition, others do, but at a scaling that is different from the Gauss incompatible case, and it may also be different from geometry to geometry within the Codazzi incompatible case. Okay, so now the questions become, well, first of all, can we somehow explain the different role of these two incompatibilities, and can we do it starting from the three-dimensional model of nonlinear elasticity, which will be non-Euclidean to include the geometric incompatibility. And so this is what we try to do together with C. But before showing you the results that we have, I want to show you this picture taken from this paper I mentioned by Eran, C, and collaborators. I want to show you this picture because I'm going to refer to some of these examples later on. And also, it's a nice picture to show. So it's another motivation to show it. So what do we see in this picture? So there's a lot of stuff there. So let me explain a little bit what we see in this picture. So each line of this table corresponds to a different geometric incompatibility. So the first example is the only one in this table where the incompatibility is due to the failure of the Gauss equation. All other examples are Codazzi incompatible. So in these two columns, so the second and the third column, you can see the target metric and the target curvature. In this first column, so these pictures try to express in a picture what the ribbon would like to do in terms of the target metric and of the target curvature. So all the examples, in all these examples, the metric is flat. So the ribbon would like to be deformed without stretching. But you have a target curvature that is incompatible with that. So for instance, in this example, the ribbon would like to undergo no stretching, but at the same time, it would like to be curved like a cylinder, but a cylinder that is wider close to this edge and narrower close to this other edge, and this is incompatible with no stretching. And so for the other examples. So in the last two columns, you can see pictures of so equilibrium shapes of wide ribbons and narrow ribbons with the corresponding internal geometry. And so in the first example, which is the Gauss incompatible one, actually it's basically the example we saw for the macromolecules. You see this helical shape that we saw at the beginning and the twisted strip shape that we also saw. All the other geometries are Codazzi incompatible, as I said. So in some cases, so for instance, in example C and E, there is no visible shape transition when you pass from wide to narrow. So here, don't get somehow confused, puzzled by these curly strips. So here, the ribbon has been cut to show that, in fact, it wants to curve in this way. So it wants to curve more close to the edges than at the center. But if you don't cut it, then you observe a very similar shape to this one. While in, for instance, in examples B and D, you see a different shape between wide and narrow ribbons. And in the paper, they also estimate the scaling at which the transition occurs. And you see that it's different from the Gauss incompatible case, and it's also different in the two cases. Okay, so now let's come to what we did with C. And so first of all, we wanted to start with a three-dimensional model. So how do we model the ribbon in 3D? So we start with a smooth three-dimensional Riemannian manifold. And inside this manifold, we somehow cut the ribbon. So we consider a submanifold S inside M and a curve inside S. So this curve will be the midline of the ribbon. So starting from the curve, we build a tubular neighborhood inside the manifold of width W, and this is going to be the mid-surface of the ribbon. And then starting from the mid-surface, we construct a tubular neighborhood inside M of thickness T. And so this is the ribbon. And now what we can show is that in natural coordinates, which are basically the arc lengths along L and the normal directions. The ribbons can be identified with this set. And in these natural coordinates, the metric has a nice expansion where you can somehow identify the two tensors that will play the role of the target metric and of the target curvature. So here, for simplicity, I assume that the mid-surface is flat, so has no Gaussian curvature. This is for simplicity, but also because in this case, we have more complete results. So I will comment about that at the end of the talk. And so what will play the role of the target metric is simply the restriction of the metric capital G to the mid-surface, while the tensor that will play the role of the target curvature is the second fundamental form of the mid-surface inside the manifold, inside M. Okay, so now the formation is simply a map from the ribbon into R3, and the energy we consider is this one. So the density W satisfies what can be considered the standard assumptions in nonlinear elasticity. So W is frame indifferent, is minimized at the identity, and therefore at all rotations. And then we assume this coercivity condition, so this growth condition from below in terms of the square distance from rotations. And the model is non-Euclidean because the density is computed at the deformation gradients times minus the square root of the metric. And so you see that the energy is zero if and only if the deformation is an isometric immersion of the metric G. So this is the same condition that we saw yesterday, so for instance, in Luciano's talk. And so if you want, because of this condition from below, we can say that the energy measures, well, control from above the distance of the deformation gradient, the distance of the deformation from being an isometric immersion of the metric capital G. Okay. So now what we would like to do is to understand the behavior of this energy, or better of its minima, of its minimum and of its minimizers, as both T and W goes to zero, with T much smaller than W. Okay. Yeah. Sorry, can you say it again? Yes. So small g and these metrics are the target metric. And yeah. So at the moment, this could be anything. So in the theorem, they can be anything. So you can prescribe any metric and any target metric and any curvature tensor. And then we are going to have results in the case when these two matrices are incompatible. Well, if they are compatible, then the minimum is just zero. Well, at the limit, because... Yeah, so in fact, I'm very happy that Eran is here, because if you have questions about also how these ribbons are built, we can ask directly him. Yeah, but from a mathematical point of view, it can be anything. Yeah. Okay, so now let me come to what we proved. So what we do is to, well, compute gamma limits of this energy, of the three-dimensional energy, with different scalings. And then from the knowledge of the gamma limit, we can deduce several properties of minimizers. Well, first of all, the scaling of the minimal energy and several properties of minimizers. So I decided to present the results in a rather informal way, so without showing you the expression of the gamma limits, but presenting directly the properties that we can deduce on the minimizers, because I think this is more effective. But if you want more details, I will be happy to say more. Okay, so it's a bit informal. So the first result that we have is for Gauss incompatible ribbons. So we assume Gauss incompatibility So, first of all, incompatibility in these results matters only along the midline. We are assuming to be in the flat case, so the Gauss equation would simply mean that the target curvature has determinant equal to 0. So when we assume Gauss incompatibility, this means that we are assuming the target curvature to have determinant not identically 0 along the midline. Okay, so under this assumption, we can show that the minimal energy, so this is the three-dimensional energy that I've introduced before in the previous slide, the minimal energy always scale as the minimum between w to the power 4 and t squared. So there is some transition when t is of order w squared, as we saw in the example, okay? And then we have, well, we can show some properties of the minimizers, but let me focus on the behavior of the second fundamental forms of minimizers, because this is where we see the change of shape. So for narrow ribbons, which means that t is much larger than w squared, we can show that the second fundamental forms of minimizers go to the target curvature. While for wide ribbons, we can show that the limit is always different from the target curvature. And so from this result, we can conclude that there's always a shape transition when you have Gauss incompatibility at the scale in t of order w squared. And somehow the change of shape is manifested in a different limiting second fundamental form. So here, let me stress, so I'm going to say something more about that when I speak of wide ribbons, actually what I mean is that we take two consecutive limits. So first with respect to t and then with respect to w. So if you want, these are very, very, very wide ribbons because t goes to 0 first and then we send w to 0. Okay, so the situation is quite clear in the case of Gauss incompatible ribbons. Clearly, as we expect, the situation is much less clear when the incompatibility comes from the Codazzi equations. So here is what we have, so what we were able to prove. So assume now Codazzi incompatibility. So the first remark, maybe, is that somehow so Gauss incompatibility is at a, so the effect of Gauss incompatibility is at a lower order. So first you see Gauss incompatibility, and then if there is Gauss compatibility, you can see Codazzi incompatibility. So it's a sort of a higher order effect. So when I say that we assume Codazzi incompatibility, I mean that along the midline, the Gauss equation is satisfied. So here we are always in the flat case, but the Codazzi equations are not along the midline. Okay, so under this assumption, we have well, rather precise result for narrow ribbons. So we can show that this is the scaling of the energy, and the limit of the second fundamental forms is, again, as in the Gauss incompatible case, the target curvature. So for wide ribbons, the result is less precise. So first of all, we do not have a universal scaling for the minimal energy, but this somehow was expected because I show you in the experiments that the scaling could be different from geometry to geometry, so we cannot expect to have a universal scaling. This is not surprising. What is surprising, if you want, is that even for wide ribbons, we can show that the second fundamental forms still converge to the target curvature. And so this is surprising because, well, we saw in these experiments from, well, of real-world ribbons from the lab, that there was a change of shape in some cases. While here, we get as limit, again, the target curvature as for narrow ribbons. So how can we explain this result? So let me add something more that we can prove. So under an additional condition that I'm going to comment on in a moment, we have a more precise statement. So if this condition star is satisfied, we can show that the minimal energy is of order w squared t squared, as in the narrow case, and the convergence to the target curvature is rather fast. So what is this additional condition about? So here I'm assuming the target curvature to have 0 determinant. So this is the Gauss equation. So 0 is always an eigenvalue of the target curvature. And so here the assumption is that there exists, so since 0 is an eigenvalue, there's always some eigenvector for the 0 eigenvalues. So the assumption is that along the midline, I can find an eigenvector for the 0 eigenvalue, which is never parallel to the midline. So this is the assumption. I'm going to comment a little bit more in the next slide on the meaning and of this condition and why we need it. Okay, so let's have a look at the examples of Codazzi incompatible ribbons, so the one from the lab. And let's check what happens in those cases to this condition. Well, this condition is satisfied in the two examples where there is no shape transition, is not satisfied in the two cases where we see a shape transition. So somehow we can interpret this condition, or better, its violation, as a necessary condition for a shape transition to occur, in the sense that when it is satisfied, we really do not see any change, for instance, in the scaling of the energy. So when this condition is not satisfied, what can we say? Well, unfortunately, at the moment, in these two examples where, we see a shape transition in the experiments, so at the moment, we do not have, unfortunately, so we are not able to identify exactly the scaling of the minimal energy. But at least in one of the two cases, in example D, we can show that the scaling of the energy is for sure different from the one we have when the condition star is satisfied, and the convergence to the target curvature is much slower. So in a sense, what we see in the experiments, in the experiments, when we see a shape transition, it's because, well, we are looking at real ribbons where the width is small but finite. And so the rate of convergence becomes relevant somehow. So if you want, this shows that the nature of the two incompatibilities, so the Gauss incompatibility and the Codazzi incompatibility, is very different. So the shape transition in Gauss incompatible ribbons is in a sense very strong, so strong that you can detect it very well from this asymptotic analysis, where we compute the limit. While the shape transition in Codazzi incompatible ribbons is in a sense milder. And so with this asymptotic study, we can only see it in a different scaling of the minimal energy and in a different rate of convergence. So this is somehow what this result is saying. So let me add some comments on this additional condition and why is relevant. And why it is relevant. So we are under the assumptions of Codazzi incompatibility. So we cannot construct, so there is no isometric immersion of the mid-surface having the target curvature as a second fundamental form on the whole mid-surface. But when this condition is satisfied, we can construct an isometric immersion of the mid-surface that has the target curvature as a second form on the midline. We can do that. So why can we do that? Because so since we are in the flat case, isometric immersion of the mid-surface are surfaces with 0 Gaussian curvature, so they are developable surface. And this vector V0 determines the direction of the ruling. So we need to know that V0 is transverse to the midline to be sure that we can construct somehow the developable surface. And so when a condition star is not satisfied, if you want, the incompatibility is in a sense stronger. So what I mean is that we cannot somehow achieve the target curvature as a second form, not even on the midline. And so what makes very difficult determining the scaling of the energy, for instance, in the two examples where we see a shape transition, is that, well, in order to do that, we should be able to characterize the structure of the relevant isometries which are the formations whose second fundamental form is only close to the target curvature, but not exactly equal to it. And so to determining the scaling, we should really somehow characterize the structure of these isometries. And this is what, at the moment, we are not able to do. Somehow, this is the difficult point. Okay. So how much time do I have, Andrea? Because we started a bit late, so I don't know exactly. Okay, so I just wanted to say a few words about the strategy of proof and the ingredients of the proof, and then I have a couple of slides about conclusions and open questions, so I think it's fine. Okay, so proof strategy. So first of all, for narrow ribbons, somehow the analysis is a bit simpler because we don't have to deal so much with the isometry constraint. So narrow ribbons for us means that T is in between W squared and W. And so what we do is to compute the gamma limit as both, so the simultaneous gamma limit as both T and W goes to 0 with a different scaling in the Gauss and the Codazzi incompatible case. And then what we show is that the gamma limits have a positive minimum, and this is what provides us with the scaling of the minimal energy. So in terms of the key ingredients of the proof, one key ingredient, as well usual in this, I mean, in this literature about thin structure is the famous rigidity estimate by Stefan, so by Frieseke, James, and Müller. We also use results about narrow ribbons in the Euclidean case by myself, together with Freddy and Paroni. But actually, with respect to these works, we also need some more precise characterization of the in-plane component of the stresses that were not needed in the previous work, because somehow in previous works, somehow these components of the stress could be neglected in the lower bound, and then from the upper bound, you could show that in fact you had ansatz with zero components, zero in-plane stress components, while here we cannot neglect these terms because it is exactly here that we see somehow the Gauss and the Codazzi deficit, so the failure of the Gauss equation or the Codazzi equation. And of course, the fact that we are dealing with a non-trivial geometry makes computation a little bit more involved, as usual. Okay. Instead, for wide ribbons, so I mentioned that beforehand, what we do is to compute two consecutive gamma limits. So first with respect to T and then with respect to W. And so when there is Gauss incompatibility, we show that the gamma limit has a positive minimum. And so this gives us the scaling. While if there is Gauss compatibility and we have the additional condition, the minimum of this gamma limit is 0. And so we can rescale further. And so in this case, well, the first gamma limit, the one as T tends to 0, is not difficult. So it's an easy variant of previous works by Marta Lewicka and collaborators. And so it leads to a non-Euclidean variant of the Kirchhoff plate. While when we scale, so when we compute the second gamma limit as W tends to 0, we get a non-Euclidean variant of the so-called Sadowski functional. So this is a functional that you get in the Euclidean case as limit of the Kirchhoff energy on a strip when you send the height of the strip to 0. And here it's a sort of a Euclidean, non-Euclidean variant of it. And in particular, in the Codazzi case, we scale further. So we need somehow a finer gamma limit of that. So this just to tell you very shortly what we do. So how we get these results. Okay, so let me come to some conclusions, and then I have a last slide with some open questions. So first of all, the first conclusion is that, well, somehow wider ribbons are more isometrically constrained than narrower ones, and in fact the analysis is more difficult for wide ribbons. So shape transitions in frustrated ribbons strongly depend on the geometry. In particular, we find out that the nature of the transition in Gauss incompatible ribbons and Codazzi incompatible ribbons is very different. So for Gauss incompatibility, we can detect very well the occurrence of the shape transition by studying, by means of this asymptotic analysis. So in particular, we proved that there's always a shape transition, and the scaling, in fact, is T of order W squared, as it was observed in the experiments and in the formal asymptotics. For Kodats incompatible ribbons, the situation is more complicated. So somehow the shape transition is milder when it occurs. And so we provided a necessary condition for a shape transition to occur, but somehow in this asymptotic analysis, we can detect the occurrence of a shape transition only in the different scaling of the energy and in the rate of convergence to the target curvature. Okay, so of course, there are many things that we don't know how to do at the moment. So the first thing is exactly detecting shape transition in Kodats incompatible ribbons. So at the moment, what we are trying to do is to look at these specific geometries from the experiments, from the real world ribbons, to see that at least in these cases, we can identify the correct scaling of the minimal energy. So that would be already something interesting to have. I briefly mentioned that our results for wide ribbons are actually limited to flat mid-surfaces. This is because for wide ribbons, we need in the upper bounds to construct isometric immersions. And in the flat case, this is more this is easier to do because we can, so what we have to do is to construct developable surfaces. So we have somehow a technique to do that. So for non-flat metrics, construction of isometric immersion is much more challenging. And finally, in the wide ribbon regime, I said that we can only compute, we are only able to compute 2 consecutive gamma limits. It would be, of course, very nice, very interesting to compute a simultaneous gamma limit, so as both T and W goes to 0, but in this range. This is a very challenging problem that it's actually still open even in the Euclidean case. So you can, forget about geometric incompatibility and just try to compute the gamma limit in the Euclidean case in this regime. This is still open because, we saw that for wide ribbons, the isometry constraint plays a crucial role. And so the advantage of taking the 2 gamma limits consecutively is that once you have passed the limit with respect to T, you are working with a Kirchhoff functional where the isometry constraint is exactly satisfied. While when you start from 3-dimensional nonlinear elasticity and you want to compute the simultaneous gamma limit, you have the rigidity estimate telling you that your deformations are close to isometries, but they are not exactly equal to isometries. And this makes a huge difference. And this is the big difficulty in computing the gamma limit. So at the moment, this is still an open problem, even without internal geometry. Okay, so this is what I wanted to tell you. And so thank you very much for your attention.
Okay. Other questions?
Help me a little bit with the length scale. So, I suppose in your results, the size of the strip never matters, what you called L.
Yeah.
And the 3 characteristic scales are the thickness, the width, and the rate at which the metric changes in the vertical direction. And you used the latter one to non-dimensionalize length because you compared T to W squared.
Yes, yes.
And so that's how you non-dimensionalize in the case when it's Gauss not compatible, because there the relevant length scale is, the relevant hidden length scale is the rate at which the fundamental form changes in the thickness direction.
Okay.
And in the Kodats non-compatible case, that's a different length scale because that must be something which is in the lateral, the rate at which kind of the metric changes in the lateral direction.
Okay.
So those are those the kind of the way you non-dimensionalize the problem?
It's a good question. So actually, I don't know. So maybe, so I think I understand your question. So actually so I don't know exactly what to answer to your question. I mean, so of course, so I understand your point that you should dimensionalize or adimensionalize. But I mean, from a mathematical, I understand that this is important in the physical problem, also to understand somehow the role of the scaling. But I mean, somehow from the point of view of the mathematical results, I mean, we're just looking at, I mean, a different, how the energy scales, the minimal energy scales. So what is the scale at which the minimum is going to be positive? So what's the order?
But I mean, so are your results? So I mean, you have, in a certain sense, you have this additional length scale, which is just this kind of the lateral length of your ribbon.
So you mean T over order W squared? L.
Yeah, and my, you know, that's perhaps a real question.
Okay.
So your results don't depend on L. Your energy scaling is you always kind of divide by L, and you look at kind of the energy per length L.
Yeah.
Or does, if you don't, then, you know, there might be more complicated phase diagram, which also involves L.
Mm-hmm.
So I think it's more than just a question of how to go from physics to
scaled by L, if you want, because it's always the energy scaled by unit volt.
So
it's always scaled by L.
It's always scaled by L.
Yes.
And you always, in a certain sense, in your mind, take the limit L going to infinity. So that length scale never interferes with the internal pattern which you see.
Yeah, I would say that no, it doesn't interfere.
Okay, but is that, I mean, is that actually something you prove? I mean, that you let.
So if I understand correctly, you would like to look at the limit of our functionals when you send L to infinity.
Yes, have a uniform scaling of the energy. Exactly, right, because only that would, in a certain sense, justify the fact that your relevant parameters are just W and T.
Mm-hmm.
So that would be a more mathematical question.
I see what you mean.
So it's make the point, it's not just a question of non-dimensionalized.
Yeah, no, I understand. So, okay, what we have, so I actually never thought about the behavior as L tends to zero, as L tends to infinity, but so our energy is always divided by L, and so for instance, I mean, in the narrow case, when we look at the gamma limits, this is a quadratic function of the Gauss or the Codazzi deficits. And then we have some small deviations from the target curvature that when you minimize, they are always equal to zero. So the minimizers are for small deviations equal to zero. So the energy is just a quadratic, so is just somehow the L2 norm squared, if you want, of the Gauss and Codazzi deficit on 0L scaled by L, divided by L. This is the minimal energy that we get. And so I would say that somehow this does not change as you change L. That would be my answer. Yeah, but thank you. So I understand your point.
In real objects behave like that. So a flat ribbon may be left-handed or right-handed.
Okay.
So so the question is, within this model, can you tell if the shape transition will be a left-handed helix or a right-handed helix?
I don't know. The short answer is I don't know.
Okay. I have another short question. Is
maybe I have another short answer.
That doesn't matter. But
okay.
About the first fundamental form, you assume that there is an axial stretch. So it's a diagonal matrix, and
The
the
examples, you
in
mean?
the exam. No, in you show G as 1 plus something 0 0 1.
Yeah, so in natural coordinates, you can always express it like this.
So the components 1 1 is not the one along the axis.
So you mean this expression? So I'm sorry.
Yes. So
So it's
is the component along the axis of the reference shape or not?
is
The component 1 1. So the G, the small
G.
the small G.
So this is the restriction of the metric to the mid surface.
Okay, but are you measuring the stretch? So the stretch, squared stretch along the axis of the ribbon or not?
Yes. I would say
Yes.
so, yeah.
Okay. So the question is why you don't have also another term for the second for the component 2 2 is because you assume that it's so small from the beginning, so it's
Yeah. So this is somehow the
it's not important.
it is the expansion, yeah, somehow of the metric in natural coordinates for x2 and x3 small.
But G is scalar or G is 2 by 2 matrix?
No, it's 2 by 2. Is this
Ah,
matrix
okay.
here?
Okay, that's what.
One.
So okay, yes.
So, yeah.
Yeah, so this is
Yeah.
is
So
a
no,
three is a 3D matrix. Okay.
Here.
Thank you. Thank you.
Yeah, no, so sorry, I misunderstood your question. Yeah.
Thank you very much, Maria Giovanna. Can I play the Japanese trick? I mean, the Japanese test
Okay.
yesterday was. I'm very fond of these results, but I want to deliberately place the discussion outside of, say, I don't want to say comfort zone, but okay. Let me. I would like you. No, I would like you to encourage you to look at some examples. Like, for example, yesterday maybe I. Expecting the beautiful thing you were saying, I showed an example. Okay, so it's a tapered bilayer. Okay, and so I would like to project this on that, or to compare somehow your results with the frame of mind of a person that builds a bilayer and sees an effect. And I have to apologize also with Iran, because in spite of my admiration, I will try to get a different viewpoint, three-dimensional, as opposed to a viewpoint really driven by the first and second fundamental form. Okay, so one observation for that example is that the shape transition, so I understand nothing about the Kodazzi one, so we talk about Gaussian compatibility. So the shape transition is even more dramatic than what you would dream to prove with the scaling. I mean, within a taper layer where the width changes from one end to the other by a factor, I don't know, 5, okay, you see the transition, okay? Okay, so this is maybe, is not a matter of scale. I don't know, maybe, there is a precise boundary value problem where one can predict a number which goes beyond scaling. And so it's a little bit this question about, maybe there's even more than scaling than that. And so inspired by this observation, now the question is the following. In a bilayer, so what are the data of the problem and what are the unknowns, okay? So if you put yourself in the frame of mind of a person that either builds the bilayer or does a numerical simulation based on 3D elasticity, so the data are the 3D metric. The data is the 3D metric, is the 3D behavior of the material. And in fact, at the interface between the bilayer, this is discontinuous. Okay, so if you start from this viewpoint, the mid-surface that emerges in the analysis is emerging, right? You don't have it at the beginning. And so this is a little bit related. I didn't appreciate very well the role of the scaling in the X3 direction that is built in your thing. But there may be a role. Okay, I don't know. My question has to do with the fact of would you see an alternative viewpoint in which the data are the 3D problem, and all this is emerging because in the starting point of your analysis, I see that in a sense there's an expectation for an emerging 2D structure that is guiding the analysis. So just a comment about that. I'm sorry, it was very long, but
So, okay, so you would like to start from, okay, capital G, but somehow you don't have, so somehow here I start from.
if I have a bilayer, right? Yeah, maybe people in the audience have a, let me say the, in the 3D case, right? So that's the 3D. And then I accept the fact that the problem will let a mid-surface emerge that maybe has the properties that Maria Giovanna is, so, but I don't know it ahead of time. And so is there a problem of different 3D, so more three-dimensional nature of the problem so that the behavior along the third direction decides what we're going to see somehow? This is...
I don't know. I should think about it. I don't know if I can say anything smart at the moment, but I understand your point. So it's something interesting to think about. I'm not sure.
You have 2 days.
I have 2 days. Okay.
No, I think conceptually, I mean, here, of course, you have this linear dependence in X3. And you have t as a parameter, so somehow the difference between the top and the bottom is of order t. So Antonio doesn't want a linear independence because that would be very hard to engineer. He just wants a jump function. You have just 2 materials. But then I think there may still be very different regimes that either you go into the regime where the difference in property between the layers is rather small, then you can use this is a kind of substitute for the thickness parameter, or you go to regime where it's really, large, or say it's even large compared to W, then I think you go into quite different regime where you're not sending, where T is not much smaller than W.
So yeah, there would be a different analysis. Thank you, Stefan. Okay.
Okay.
Thank you.
Okay, maybe I again suggest that we ask other questions later, and thank Maria Giovanna again.